Hello. Yes, hello. Good morning to you all. I hope you are all fine. Yes, so it's quite unfortunately we cannot meet in the classroom today to do to conduct our physical class. So I did this video for you to get the opportunity to learn the capacitors and capacitance. Like I said, find time to watch this, and when we meet in the classroom, you'll just be left with more like questions and discussions. So once you watch this, I'm optimistic that it become easy to complete it when we get to the classroom. Right. So before we understand the capacitors and capacitance, we first need to know what is termed as what the electrostatic field. Do you get it? You see, a capacitor basically have two plates, right? Which is shown in the figure below. So we have two plates there. That is the plates called the A, are you okay? And we have plate 2 called the B. All this line is representing the B plate, which is more like negatively inclined. So we have negative charge on the B plates, and we also have what? Positive charge on the plates. Do you get it? So this region, right, where we can identify the line of field, right, all this region where we can see the line of field, do you get it, can be termed as what? As the electrostatic field. Are you okay? So if you look at it, it said any region such as the figure shown below, right, in which an electric charge experiences a force, are you okay, is called electrostatic field. So all this region over here, right from the plate A all the way to the plate B, right, can be termed as what? As electrostatic field, right? So such a field may be represented in what? In magnitude and direction by line of what? Electric force. So these are the line of force, right? So those fields have been represented with what? Magnitude and direction. And the direction is more like moving from the positive plate all the way to what? To the negative plate. So we have those lines as the lines of what? Of electric force. Yes. So maybe when you watch this side, watch again. If you don't get anything when we come to class, you give me. I'll assist you towards to understand based on the questions you ask. Are you okay? If you are okay, that's fine. Okay. So the electric lines of field are continuous and start and finish on what? On point of charges. So they are continuous. Do you get it? Looking at this one, there is an infinite charge somewhere, or there's a charge placed at a particular place, a negative charge somewhere, which is creating the line of field all the way towards to a negatively charged atom, right? So with this image 2 we can see that the line of field are moving from what? From the positive charge towards to a negative charge. So he say that the electric line of force, right, or which is also termed as the electric flux lines, are continuous and start and finish on what? On the point of charge. Do you get it? And they do not cross each other, right? When they are moving, they cannot cross each other. Like this one moving all the way to cross this. That's not how they behave. They are always in line. Do you get it? They don't cross each other. So when a charged body is placed close to what? To an uncharged body, an induced charge of opposite sign appears on the surface of what? Of the uncharged body. This is because of what? Force from the charged body terminates on its surface, right? It's because the line of force from the charged body hot terminates on its surface. You get it? So all I is trying to say is that if, let's say, an uncharged body is placed just, let's say, at any point within the charge, right, what is going to happen? Sorry, an induced charge of opposite sign, right? So assuming this was neutral, it was placed just close to what, to this charge, right? So an induced charge of what, of opposite sign appears on what, on the surface of the uncharged body. So this one was first uncharged, and now we did what, it was closer to it, so a charge was induced into it, and that's why you are having the negative charge. That's what the statement is trying to say, right? So this is because of line hot. This is because lines of force from the charged body hot terminates on its surface. So because of this, normally we also have like force of attraction over here. Do you get it? But if, let's say, I have a charged body, right, and I place, how do you call it, a positive charged body closer to it, right, then there will be a force of what, repulsion. Do you get it? They are going to be a force of repulsion. They are not going to what, attract each other. Do you get it? So that is more like the law of attraction and repulsion, or like poles and unlike poles. So when we have unlike poles, they repels, right? But like poles what, attracts. So there is always a force of attraction or what, or repulsion based on the type of charges, whether they are alike or they are not alike. Do you get it? Yes. So he said that the force of attraction or repulsion between two electrically charged bodies is proportional to what? To the magnitude of what? Of their charges, and inversely proportional to the square of the distance separating them. Yes, so that is more from the Coulomb's law. Okay, so F is basically equal to what? Q1 times Q2. That's the two charges, all divided by what? The square of the distance between them. Do you get it? And the K is a constant, which is giving us 9 times 10 with the power 9. Definitely, I believe someone will ask you, say, if you give us a question, are you going to provide us with a constant? Yes. We are going to give you a formula sheet as well, and also a formula sheet which contains, like, let's say, complicated formulas which you cannot memorize. Do you get it? You don't need to memorize this in your brain, like constants and complicated formulas. You don't need to memorize them. Do you get it? When it is time for exams, we normally provide them. Are you okay? Yes, sure. Okay, so let's take a typical example here. If, let's say, I have what? I have, sorry. If, let's say, I want to find the force, right, between two charged spheres, right, in air with their center being hot 16 millimeters apart. Do you get it? So I have a charged body here and I have a charged body here. The first one is more like plus 1.6 microcoulomb, and the second one is plus 1.6 microcoulomb, right? And I have this to be plus, this to be plus. So I want to find the force, which will be a force of repulsion in the first place. So I want to find the force that exists between them. So it's going to be the product of the two charges, Q1 and Q2. They are all the same. That's the reason why we have 1.6 times 10 with the power minus 6 squared. Are you okay? All divided by the square of their distance, which is 16 times 10 raised to the power minus 3 all squared. Do you get it? And this is more like the constants. So at the end, if you should compute for it, you are going to get 90 newtons. So you can try your hands on it with your calculator and find out. Okay, so what is the electric field strength? That's what we are talking about now. What is electric field strength? Do you get it? So electric field strength, it tells us how strong the electric force is at a point within the field, right? So we have the, how do you call it, electrostatic field, as I showed you here. Okay, so these are more like the field of the region. So how strong the field is at that particular region is what is termed as what, as the electric field. So the line of force here, how strong they are at the particular location, right? So it's more like how strong the electric field is. So let me write it here. Maybe you cannot hear me well. So it is more like how what strong, right, the electric force, right, is, right, at a point. Do you get it? So how strong the electric force is at a point is what is termed as what, the electric field strength, right? And if we should ignore all fringing effects, like fringing, when you say fringing, fringing is basically, let me show you this one. Sorry, let me move backward. Yes. So if you should look at this diagram, right, you see that there is one line of force bulging, coming out this way. There's another one to bulging out. That is more like coming out. It's not straight, right? So they introduce the fringing effects. Do you get it? So if, let's say, this, how do you call it, effects is appearing between two plates, it affects the electric field strength. That's the reason why, if you should look at this statement, it says that by ignoring fringing between the two plates of the capacitor, right? If you should dive deep into it, which at your level, there's no need to dive deep into it. So if you should dive deep into it, then it's going to have an effect on what? On the electric field strength. So if you should ignore it, then the electric field strength can be equal to what? The voltage across the plates of the capacitor, right? So these are the two plates of the capacitor. So the voltage across it, which is V, and the distance between the plates of the capacitor as D, right? So the D represents what? The distance between the plates and the of the electric field, right? And the V, right, also represents the potential gradient, right? That's the voltage across the plate. So he says that electric field strength is also called potential gradient. Sorry. So let me take it again, or you watch the video again. So he says that the V, right, is more like the voltage across the plate of the capacitors. Then the D is what is the distance between the two plates, right? So the electric field strength can also be termed as what? As the potential gradient. The V here is the potential difference, right? Potential difference across the two plates of the capacitor. So the another term for the electric field strength is also what? The potential gradient. Yes. So let's move on. So the next thing that we need to talk about is the capacitor, right? Yes, I'm coming. Yeah, this side. I don't know why my slides keeps on jumping. I think we are here. The capacitance. Yes. So what is capacitance here? Capacitance is what is the property, right, of the capacitor that determines what, how much charge corresponds to what, to a given potential difference between the plates of the capacitor, right? Yes, so that's it. So the property of what of the capacitor, that determines how much charge, right, corresponds to a given potential difference across the plates of the capacitor. Are you okay? Yes, so that is more termed as what as the capacitance, and generally is given as C equal to what Q on what on V. So you should take note of that. Do you get it? You see, the the SI unit, which is more like the farad, is so high, very very high, right? So most of the time we need to represent them in the micro, pico, and even nano, right? You normally represent them in micro, pico, and nano because the unit or the value, if we should leave it in farad, is so high. Do you get it? Yes, that's it. So he said the unit of capacitance is what is farad, which is defined as what as the capacitance when the potential difference of 1 volt appears across the plates when charged with what with 1 coulomb. Do you get it? So if let's say I have it's using the units to what to explain this one. So this is more like coulomb and what and volts. So he says that is defined as what the capacitance when a just one potential difference of volts appears across the plates when charged with what with 1 coulomb. Do you get it? So that's more like the unit for capacitance, right? And what's a capacitor, right? So the capacitor is what capacitor is a device, right, constructed to what to possess capacitance. So any device that possesses capacitance is called a capacitor, right? That is the term there. So all the devices that possesses capacitance are termed as what? Are termed as capacitors, right? Okay. They can also be called what? Condensers, right? So you should take note of this as well. So capacitors can sometimes be called condensers. And when you pick the two plates of a capacitor, right, there is a material in there which is more like an insulator. So let's say I have plate A and plate B, right? So there's a material in there which is more like an insulator, right? And that is called the dielectric, right? So the capacitor what possesses a material between the two plates, right? And that material is termed as what? Dielectric, right? So these are more like some schematic diagram of capacitor. We have the variable capacitor here and we have the fixed capacitor at this point. Okay, so what next? I think I'm skipping the slide. Let's move on to this. We are here. So the charge, right, Q, can also be measured with what? Or can be computed as the current times time. We've made this before during our first class in applied electricity, where we said the current, which is more like the flow of charges, right, equals to what? The charge with respect to time. So the rate of flow of charges, where we even said the I on dq. We use small letters like the I on equal to what? Dq on what? On dt, right? So it's emerging from that side. Charge, when charge flows, they create what is termed as the currents, right? That's the reason why we relate it with what? With the current, right? If you have any question when we come to class, you can ask. Now, with this, I'm optimistic that the questions here now becomes so simple, right? What are the questions here? Oh, sorry. So the questions here become so simple. So it says that we should what? We should determine, sorry. So this will not be an edited video. It's going to appear just as it is, so please bear with me. There's no time to edit, and I just want you to get access to it. Once you are done, I'll quickly delete it within the course of the week, right? That's next week. So you need to watch it well, and at the end, that's all. Right. So we're at this question. Do you get it? These two questions. And the first question says that we should determine what the PD across the a 4 microfarad capacitor when charged with 5 microcoulomb. So we have the capacitance as 4 microfarad, and we have the charge, right, as 4 microcoulomb. So in that case, we said the C is equal to what? Q on V. So when we are looking for the charge, we just make what? We are looking for the potential difference, that's the voltage, right? So we just make change of subject, and at the end we are going to get C equal to what? Q on what? On C. V equals to what? Q on C, right? We just substitute the 4 microfarad. We just substitute what? The 5 comes up there, so 5 millicoulomb, right? All on what? On the 4 microfarad to get the answer. Do you get it? Yes, that's fine. So the same applies to this one. This time, you see, we should find the charge, which is more like the Q, right? So what will be Q here? Q is more like the VC. So we have the voltage there, which is 2 times 10 to the power 3. Then we have times the capacitance, which is more or less the 5 times what? 50 times 10 to the power minus 12. Do you get it? Yes. Once we get that, then we compute it. It's so simple. It's nothing that you need to worry yourself about. It's something that I believe everybody can do, right? So what is electric flux density? Before we talk about the electric flux density, we need to know what electric flux is, right? So the electric flux, it tells us how much how much the charge, right, exists at what? At the surface, or the number of charges that is found within the electric field. So that's what the how do you call it? The flux is about. It's basically charge, right? So it's also measured in coulomb. So we are saying that the flux here, the flux is basically the number of charges that are present on the lines that we showed through the surface. Do you get it? So all I'm trying to say is that I have, let's say, 2 plates here, right? So how many charges, right, are within the line of field here from positive to negative? You get it? So how many charges are found there? That's more like flux. Basically, or to make things simple, the flux is more like charge, right? Flux and charge are more like related. So they are measured in what? They are measured in coulombs. Are you okay? Yes. So when you get to class, if you are struggling with anything, you just let me know. I'll explain further to you. Right. So when we say the electric flux density, right, which is the D, right? So the electric flux density is giving us the amount of flux, right, that is passing through a defined area. So mathematically, it's giving us D equals to Q on on A. So that's more like the flux density. So because the flux is more or less a charge, right? So we can also call it charge density. Okay, so you should take note of it. So the electric flux, electric charge are virtually the same, right? So because of that, the electric flux density can also be termed as what? As a charge density. Okay, let's move on. What is a permittivity? What is permittivity? So permittivity just explain how easily the material, right, allows electric field lines to pass through them. So I have two plates here. I have plate A and plate B, right? So how easily, more like how easily, right? The line of field, right, passes through the two plates. Are you okay? So how easily a material allows the line of field to pass through them. So that's more like the permittivity, right? So at any point in an electric field, the electric field strengths maintain the electric flux and produces a particular value of electric flux density at that point, right? So for a field established in a vacuum, that is when we have the field in a vacuum, a free space. Do you get it? Then the ratio of the flux density to the electric field strength is equal to what? Is equal to that permittivity constant, which is more like this is a constant and it's permittivity of what? Of free space, a vacuum where there is no air, where there is no medium, right? So that is termed as the permittivity of a free space. Do you get it? And what's the unit? It's giving us 8.85 times 10 raised to the power minus 12 farad per meter. Yes, but we can have a permittivity in a medium, right? And the permittivity in a medium can be given as as the ratio of the flux density to the electric field strength multiplied by the epsilon, right? Where this epsilon is more or less the absolute permittivity, right? So the epsilon here is the absolute permittivity, and the absolute permittivity is obtained from what? From the relative permittivity and the, how do you call it, permittivity in a vacuum. That is more like the relative permittivity is comparing the two permittivities, where we have the absolute permittivity on what? On the permittivity in a vacuum. So in that case, if I want to find the permittivity, right, in a medium, or in example A, right, then I will say that the D on E equals to what? The absolute permittivity. And we know that the absolute permittivity, right, we know that the absolute permittivity is equal to what? The permittivity in a vacuum and the relative permittivity. So in that case, if I want to find the permittivity in a medium, then I'm going to get what? The epsilon naught on epsilon r. Right. Yes. So you should take note of that one as well. This is more like the relative permittivity of some mediums or some materials. Right. We have the air, we have the diamond, mica, polyester, quartz, the silicon dioxide, and water. So they are showing the relative permittivity. Again, when you are asked to solve questions, definitely you'll be given the relative permittivity. Nobody will be asking you to memorize this table, right? Or nobody's asking you to memorize the table. We've talked about this term already, the dielectric strength, right? So it's an insulating material that is found between the two plates of a capacitor or any conductor. right? It's an insulating material, and it has a very high resistance, right? That is more like it's preventing the charge to move easily from what? From the positive to what? To the negative plates. Do you get it? So it says that the insulating medium separating charge surface is called the dielectric, which we've talked about. Do you get it? Compared to conductors, they are hot. The dielectric has a very high hot resistance, right? So the resistivities in dielectric material are so high, and that's the reason why they place them between two conductors like what? Like the two plates of a capacitor. Good. So let's move on. So based on what we've talked about so far, I believe you can solve more or less, how do you call it, the example which is found here, right? And what this example is saying, you see that we have what? We have a rectangular plate measuring 20 centimeters to 40 centimeters, right? And it carries what? A charge. So here we can compute for the area, right? So it's a rectangular plate, so the area can be equal to what? 20 times 10 raised to the power minus what? 2. 20 times 10 raised to the power 2 times what? Times 40 times 10 raised to the power minus 2. And that can help us to get the area, right? Then once you compute for the area, we can also compute for what? For the electric charge, which is more or less the Q. Are you okay? And out of this, we can compute for the electric flux density. So the electric flux density, which is more or less D, is giving us what? Q on A. So you just substitute the result that you get to get the answer, right? So you can try your hands on it. The solution is in the handout as well. So you can also visit the handout and check the solution. And it says that if the plates are spaced 5 millimeters apart, right? So this is more like a D, which is 5 times 10 raised to the power minus 3. And the voltage between them is 0.25. So this is more like a V, which is 0.25 times 10 raised to the power 3. So you should determine the electric field strength. So E. So what will be E? E is basically going to be what? The V on D, right? Yes, that's it. So at the end, I'm going to get the 0.25 times 10 raised to the power 3, all divided by what? By 5 times 10 raised to the power minus what? Minus 3. And that can help me to compute for my electric field strength. So like I said, the solution is in the handout. If you come to class and you don't understand anything, you just let me know. We are going to spend some 5 minutes, 10 minutes to answer questions when we come to class. Okay, so you see, how did we get this formula for capacitance? They are obtained from, let's say we have C equals to what? Q on V, right? We have this one there. But you know that D is equal to A on what? A on what? Like D equals to, no, not A, sorry, it's Q on A. Do you get it? So at this point, if let's say I want to find my Q here, then Q can be equal to what? dA, right? So I substitute the Q in this capacitance equation, and what do I get? I'm going to get my C being equal to what? dA on what? On V, right? Yes, but what is the electric field strength as well? We know that the V equals to what? The ED, right? So the V is equal to the ED. So I can substitute it into what? Into my equation again, where I have the V. And at the end, what do I get? I'm going to get C equal to what? C equal to dA on what? On ED, right? But what about this one? This one is more like the constant, the permittivity constant. Can you see that? Yes. So at the end, if let's say I want to find C, C is given as the epsilon not epsilon RA on what? On D. So that's the capacitance. That's the reason why we are getting this formula for capacitance, which is measured in farad, right? So this is more like for just two plates, right? If you have multiple plates, then we need to attach n minus 1 to it, where n here represents the number of plates. Where n represents the number of plates. So you should take note of it. So at the end, we can get the C equals to what? Epsilon naught epsilon R A into bracket n minus 1 or D. So this one are more like in a medium, right? But if we have a vacuum, then we can write C equal to what? Epsilon naught A on what? On D. That is for just two plates, and the permittivity is more like in a vacuum or a free space. But if we have how do you call it, a vacuum with multiple plates, then we are going to get C equal to what? Epsilon naught n minus 1. Let's put the A there. So epsilon naught times A n minus 1 all divided by what? D. So that's the capacitance when, let's say, it's in a vacuum and we have multiple plates. Okay, sure. So at this point, there's also one thing that I need to tell you here. You are not always going to see rectangular plates sometimes. So sometimes you can get a circular plate, and you should know when it's a circle, then the area is obtained from what? 2 pi r squared. Are you good? Yes. So in the question, you'll be given the distance, the diameter or the radius. So once you are given the diameter or the radius, it can help you to compute for the area. Are you okay? So you should take note of it. So sometimes they can give you a circular plate. Okay. So let's put that one aside then and focus on the next example, which is more or less down here. Okay. So let's focus on the next example here. It says a parallel plate capacitor has 19 interleaf plates. So this is more like the N. Are you okay? So the area there is given in a square, right? Something like a square. So the area there, let me clean some part of my board so that I'll get some space to write. That's fine. Okay. So the area there is given as 75 times 10 with the power minus 3 times 75 times 10 with the power minus 3. Do you get it? So that will help you to compute for the area. And it's separated by a mica, right? A mica sheet of thickness. So this is more like the D. So the D here is given as the 0.2 times 10 to the power minus 3. So assuming the relative permittivity, that is ER, is given as 5, right? You should calculate for the capacitance. So in that case, we have the A, we have the N, we have the D, and we know the epsilon naught. So in that case, what should be the capacitance? C can be equal to what? I'm going to use the epsilon naught, epsilon R. Then we have the A, and we have N minus what? 1, all divided by what? By T. So this is the formula that you are going to use. So you know this one already, which is 8.85 times 10 to the power what? Minus 12, right? Then this one was given in the question, which is given as what? As 5, right? Then you know the A, we compute it from the 75 millimeters. And we also know the N, which is 9. Then the distance there is more or less, how do you call it? The thickness, right? So this figure here is showing a capacitor with multiple plates. So this is a capacitor with multiple plates, right? You can see it in your handout as well. Okay, that's fine. Yeah, we are gradually getting to the end of the capacitance and capacitors, right? So let's move on. So here, assuming I have, how do you call it, a capacitor in parallel like this, right? What is going to happen? At this point, see, they are connected, the charges are more like positively connected to either. If I have this one, I have, let's say, positive Q1, positive Q2 at this end, and positive Q3 at this end. So here it's more like positive, positive, positive. So if you look at how they are connected, it means that the charges are not the same, right? So charge, if you have a charge here, it cannot move from this place to this place, right? Charge cannot move that way. So in that case, when the charge gets here, or when the current gets here, the charge are separated. So in all of that, I'm trying to say that when we have a capacitor in parallel, then the charges are not the same, right? But the voltages are the same. The V here is the same as what? V here is the same as V here, and is the same as the V at this point. Do you get it? So in that case, if let's say I want to compute for the total capacitance, I need to use the charge, because I know that they are not the same. So the total charge is given as what? The Q1, Qt equal to what? Q1 plus what? Q2 plus Q3. But what can we say about Q? Q is the same as Vc. So let's say I have Vc equivalent here. Since the charge or the voltage are the same, they are all going to be V. So Vc1 plus what? Vc2 plus Vc3. So if I should divide all the terms by V, right, then what do I get? I'm going to get the Ceq equals to what? C1 plus C2 plus what? C3. Yes, so that is the equivalent capacitance, right? So all I'm trying to say is that when they are hot, they are in parallel, then we sum the capacitance. So it's more like treated as resistance in series. You've done resistance already. So R1, R2, and R3. So it's treated as what? As resistance in series. Do you get it? Yes. So at this point, since the charges are not the same, we always find charge division, more like Q1. Let's say I have been given capacitance, and I want to know the charge over here after getting my total charge. Let's say the total charge in this circuit is Qt, and I want to know the charge Q1 on capacitor C1, and I go for charge division. So what the charge division is saying, let's prove it. We say that the Q1 can be equal to what? V what? C1, right? That's it. But what about V here? V can be represented with what? The Qt divided by what? The C equivalent. That's the total capacitance, right? So we have the C1 here. So basically it's simply Qt equals to what? C on what? C1 plus C2 plus C3, or let's say C1 divided by C1 plus C2 plus C3 times Qt. So that's the charge division. So the charge division is treated as what? As voltage division in resistance. Voltage division for resistance in series, right? So if you don't understand, just call a friend. Definitely some of you understand what I'm talking about and they will assist you. But if more or less you still don't understand, when we come to class we have a more talk on it, right? Then we also have capacitors in series, right? So when the capacitors are in series, what's going to happen here? When they are in series, you see we have positive Q here, negative Q here. So assuming there are no losses, right, the charge that comes from this plate moves onwards or migrates to the negative plate, right? And assuming there are no losses, the same Q, because they are more like a force of attraction, it can migrate towards to C2 capacitor, right? Then it moves to the negative plate of C2, and that same charge cannot can move to what? Can move to the C3 because of the force of attraction. Are you okay? So we say that the charges Q here can migrate to Q here, can migrate to Q here, as the circuit works. So when we have this one, we see that the charges are the same. Q1 equals to Q2 equals to what? Q3. Right? But the voltages are not the same. So the V can be what? Or the VT can be equal to what? V1 plus what? V2 plus V3. Can you see that? Yes. So in that case, if let's say I want to find the total capacitance, then I'm going to get, we know that V is Q on C. So since the voltages are the same, I'm going to get Q on what? CE equivalent equal to what? Q on C1 plus Q on what? C2 plus Q on what? C3. Assuming the Q are 1 because they are the same, they are going to get 1 on what? CEQ equals to what? 1 on C1 plus 1 on what? C2 plus 1 on what? C3. Can you see that? And this, if I want to find the C equivalent, what do I have? I'm going to get C1, C2, C3 all divided by what? C1, C2 plus C2, C3 plus C3, C1. You understand what I'm saying? So there's no need to move deep down into this. If you should solve this one, that's what you are going to get. Right? So you see that the voltages are not the same. Right? So in that case, we have voltage division here. So if I have this one, for instance, I want to find the voltage across the C2 capacitance. Then let's say that is going to be what? That is going to be, what will it be? It's going to be the V2 equals to what? Q on what? On C2. Right? But what is Q? I can represent Q with what? Let's say 1 on C2. I can represent it with the CE equivalent, right? Times the VT. Because we know that Q is equal to what? K is equal to VC, right? So I can represent it like this. And this one is the same as what? 1 on C2. 1 on C2, sorry. 1 on C2 times what? Times what was C equivalent here? It was C1, C2, C3, all divided by what? C1 plus C2 plus what? Sorry. C1, C2. So we have, let me delete this one. So pen, right? So it's C1, C2 plus what? C2, C3 plus C3, C1 times the VT. Can you see that? So the C2 cancels the C2 here. So at the end, what do I get for the V2? V2 is equal to what? C1, C3 all divided by what? C1, C2 plus C2, C3 plus C3, C1 times what? Times the VT. Right, so what do we see here? If we did current division in resistors, right? So this one is also more treated like current division in resistors, where we have the opposite divided by what? If let's say I have 2 capacitors here. A typical example is if I have 2 capacitors here, right, in series. I have C1 here and let's say C2. Right, if I have C1 and C2 here like this, sorry, and I want to find the voltage across C1, right, I want to find the voltage across C1 and I'm given the VT, then what will it be? We are going to get the V1 equals to what? The other capacitance, which is C2 divided by the sum of the capacitance, which is C1 plus C2 times what? Times the Vt. So that's more like the voltage division. And this is treated more like opposite to what? It's the same as finding the current in what? In resistance. If you have the two resistance R1 and R2 and it's more or less parallel to a current source, then it's the same thing as treating the capacitors in series. I think I've talked more on this. If you don't understand anything, when we come to class, you just ask your question and I'll explain to you. So let's solve this question, then we move on to the next slide. Right. So let me delete all my writings here. I think I'm consuming more space. Or better still, let me do something. Let me discard this. Okay, let me discard it. Right. That's fine. If you don't understand it, reverse and watch the video again. Wow. Okay. So let's draw the capacitor here. Coming. Pardon me, like I said, this video will not be edited, right? So just watch it as it is. Okay. In the course of the week, I need to delete the video. So watch it before the week goes to an end, right? Okay. So sorry, pardon me. Let me just open my PowerPoint again. Okay. So if I can recall, okay, it has appeared. So there's no need to record anything again. So let's continue by what? By solving the question. Okay, so I'm going to solve this question, right? So he says that we should find the total capacitance in the circuits for this circuit. So you see, these two are in what? Are in parallel. Let's call it C1 and C2, right? And in series with what? C3. So in that case, what will be the CEQ in just one formula or one equation? So we are going to get parallel first. So we have C1, C2, all divided by C1 plus C2. Can you see that? Right. Sorry. I'm treating it as capacitors in resistors in parallel. Sorry, this is wrong. Let's correct ourselves. Right. So what will it be? It's going to be this is what I wanted to write. So we are going to get C1 plus C2, right, as 1. Then now since it's series with the 15, I'm going to get C1 plus C2, C3, all divided by what? The C1 plus C2. That was the resultant there. Then we have plus C3. Yes, I believe you understand. So this one is more like 5. So it's more like equal to 5 times what? Times 15, all divided by what? 5 plus 15. Because the C1 plus C2 will add up to 5. Right. So 5 times 15, 5 plus 15. And that gives the equivalent resistance in microfarad. So you can compute for it and you see the answer there. Right. I don't have a calculator here to compute for it. And I don't want us to spend more time on this video too. So you compute for it. Are you okay? Yes. Now let's assume this 3.67. Let's assume. So it might not be 3.67, but let's assume 3.67. Okay, that's fine. So we also want to find, if we be able to find the first one, it says you find what? the equivalent capacitance. So that's the first one. The second one, is the voltage across the QR, right? So this voltage, that is, let's call it V1. So what will be V1 here? So V1, we are going to use voltage division. So the opposite capacitance, which is more or less, what was the value there? It was 5 microfarad, right? So 5 divided by the sum of the resistance, which is 5 plus 15 times what? Times 240, right? Yes, so that's going to give us the V1. And I think with this one, you're going to get 60. So here is going to be 60 volts. Right. Yes, that's fine. So in order to find the charge for each capacitor, right, we can also compute for what? The voltage here. Since it's left with just the V2 here, it's very simple. What you need to do, you can use this formula. Let's say V2 equals to what? Equals to the 15 divided by what? Divided by 5 plus 15 times 240. Right, you can use this one, or you can say that V2 is equal to what? 240, that's the total voltage, minus what? Minus the 60, right? Because we know that the Vt is equal to what? The V1 plus V2. We have only two voltages here, V1, V2, right? So that's it. You can use any of these two. You can use any of these two to get your answer. Are you good? Yes. So that gives us the voltage across the QR. No. This is the voltage across the QR. So let's say QF. So the voltage across the QF is also computed from this one. And I think the answer should be the 180. Yes, because 60 plus 180 is going to give us 240. Right, so this is more or less 180. So when you get this one, then it becomes easy to find the capacitance, right? Because you know that C1 equals to what? C1 equals to, we have Q being equal to what? VC, right? So what will be C1? So C1 can be equal to what? Q on what? Or let's say Q1 on what? On V1. Right, but the question is we should compute for the charge. So in that case, we rather need to say Q1 equals to what? C1 V1, something like that. Do you get it? So we know the capacitance here, C1, we know C1 here, and we know V1. Sorry, this is more like V2. So C1 V2, right? V2 is here. V2. So we have C1 V2, right? And that's the capacitance. So if I want to compute for it, in summary, if let's say I want to find, let's say Q1, then it's going to be what? The C1, the capacitance there, which is 2, which in our case is 2 what? Microfarad, right? Times the V2, which we had as what? As 180. Do you get it? Yes. So that's it. Then what will be Q2? The Q2 is more like the charge across the capacitance C2. So it's going to be the 3 microfarad times what? Times the 180 again. Then we have the Q3 being equal to what? The 15 microfarad times what? Times the 60, right? So when you are computing, the farad is SI unit, so you don't need to bring it inside, right? You don't need to bring it in. All you need to do is 2 micro times 180 and so on and so forth. I think that's fine. So let's talk about the last 2 slides. Then we'll call it a day. Right. So here you see, we have dielectric strengths. Because we have dielectric in the material, we have dielectric strengths. So the maximum amount of field strength that a dielectric can withstand, right? It's what is termed as the dielectric strength. And because we want to differentiate it from the electric field strength, we always attach M to the subscript. Are you okay? Yes. So let's solve this example here. And with this example, it says that what? It says that the capacitor is constructed from a capacitance of, so we have C here, right? Then at this point, we have V at this point, V here too. Do you get it? Yes. So it can be Vm, it can be V, any of them is correct. Then here, we don't need the safety factor, right? We don't need the safety factor. It's more like in construction. When we say the safety factor, it is how much hot or how much higher a capacitor is designed to handle the voltage, right? Compared to the normal operating voltage. So we have a capacitor, we have an operating voltage that we've added the capacitor to handle. So if I want to find the ratio of the operating voltage to the rated voltage. Sorry, so the safety factor, right? So we have the safety factor being equal to what? The rated voltage to what? To the operating voltage. So when a manufacturer designs it, right, he designs it with what? With a rated voltage. Do you get it? So once he designed it with the rated voltage, if the capacitor is operating, right, is asking us that, or is saying how much high, right, the capacitor, or how much the capacitor can handle voltage, right, compared with the rated voltage. Okay, maybe you might not get it well, but you can research more on the safety factor. Then you get a better understanding of it. Do you get it? But we don't need it in this question. We don't need it in this question. Maybe it's just there to trick you or something of that sort. Right. So let's proceed. So with this one, I want to find the thickness. Like I said, I have the capacitance here, right, which is 0.2 microfarad, and I have the voltage here, right. Then what again? I've also gotten the dielectric strength, that is the EM. So if I want to find the thickness of the mica, right, then I can use the EM equals to what? The Vm on D, right? Why? Because I know the voltage, which is the 1.2. Then I know the, how do you call it? 1.25 here. So 1.25 times 10 to the power 3. And I also know the EM here, which is 50 MV per M, right? I'm looking for the D. So just D equals to what? EM Vm. So it's going to be Vm, sorry. So the D is basically going to be what? D is going to be what? It's going to be I'm going to make D the subject. So it's going to be Vm on what? On EM. Yes, that's it. Right. So once you substitute in there, it will help you get your D. Are you okay? Then you come and use this formula to find your area. So you say you should compute for the area. Are you okay? We're going to use C equals to what? epsilon naught epsilon r A. We said it's just two plates, so we don't need to bring the n minus 1. All divided by what? By d. So this one can help you get your area, where we have the CD on what? Epsilon naught epsilon r. Do you get it? So the A can be CD divided by epsilon naught epsilon r, and all are found in the question. We have the ER given in the question here, right? Then we have the capacitance, the C, which was given in the question. Then the D, we computed for our D, so that's the D, and this is more like the constants, right? That's fine. So another formula that you need to know is the energy, right? So the energy stored in the capacitor, right? So that one is giving us half CV squared. So that's the energy stored in the capacitor. Okay. So if I want to find the power dissipated in the capacitor, I can say that it's equal to what? The energy multiplied by time. Because we said energy is equal to what? PT. Not multiply, sorry, divided by time. We said energy is equal to what? PT. Are you okay? So if I want to find the power can be equal to what? The energy divided by what? Time. So with this one, I believe you can solve the example 4.10, where you see that we should determine the energy stored in what? In the 3 microfarad capacitor. Right, so in that case, what will be C? So at the end, we are going to get W equal to what? Half CV squared, right? Where we have the C being equal to what? 3 micro. Then we have the V being equal to 400. So I can compute for it and I'll get my what? My energy. Then the next question is that we should also find the average power developed if this energy is dissipated in what? In a time of what? Of 10 microsecond. So here we are going to use the P equals to WT. The W that you were able to find here, you must divide it by the time. Are you okay? Sure, that's fine. So they are all in the handout. So try your hands on it and look at the solutions there. Now the last thing that we will talk for the day is the discharging of capacitors. So let me give you a sketch here. So let's say when I have a capacitor, right? And let's say I connect it to a voltage source. Then the capacitor begins to charge, right? So assuming I have a resistor here, right? So with this one like this, the capacitor is charging. So it can be completely charged. So if I just switch it to point B, so let's say it's at point A now. So assuming I switch it to point B, right, then the capacitor begins to discharge itself. A typical example is your charger. Some of your chargers, you have light there, right? So as soon as you remove it from the socket or the main outlet, right, you see that the light will still be on, right? When the light is on, it shows that the capacitor is discharging itself into the lights. Are you okay? Because all those circuits, we have capacitors in there which discharges itself to let the light goes on for some time before it goes off eventually, right? So if I have a charged capacitor and I connect it at point B, it begins to automatically discharge itself. So a precaution needs to be taken when you are discharging the capacitor, because if you have a very high capacitor and you are discharging it, it's very risky. You get it? So when a capacitor has been disconnected from the supply, it may still be charged, and it may retain this charge for some considerable time. Okay, so for instance, let's say I have a charged capacitor, and when I remove that capacitor from the charge or from the voltage source, then we will have charges between the two plates of that capacitor, so it can stay there for some time, right? So it says that Precaution must be taken to ensure that capacitors is automatically discharged after the supply is switched off. This is done by connecting to a high value resistor across the capacitor terminals. So if it's charged here, there's a lot of charge here, and I connect it towards a high value resistor, then mean that the capacitor, the charges will discharge itself towards to charge the resistor here. Yes, that's fine. Thank you very much. And it's a long video possibly, but try as much as possible to watch it. If you don't understand anything, when you come to class, we'll have a discussion, and I believe you'll be fine. Are you okay? I wish you the best of luck. All the best. Okay.